Welcome to Spring LIB.
So, once again, welcome to a new problem. This time we're still dealing with wavelengths, and in a special case, we have a spy satellite. So we're dealing with a spy satellite. Imagine that these objects are obviously out there in outer space, and they do have lenses. So it means that the lenses can capture objects at a specific distance on the ground, if you want to think of it that way. So assume that we do have a lens right here on the object, and the distance between the item on the ground and the satellite happens to be, or we can think of this distance. This distance happens to be, we want to see it as a perpendicular distance as opposed to a distance at an angle. So maybe we'll shift the lens such that it's facing downwards, for example, and the gap, this distance right here, happens to be 160 kilometers. That's the distance we're looking at, 160 kilometers. That's the distance. And this is the Earth. So it's above the Earth. The lens is above the Earth. The focal length is 3.6 meters. If you think of the focal length, let's say this is a point right there. And there's always some light going through the focal length. We want to try to be as accurate as possible. So if you have parallel light going that way, it's going to bend, and this distance right here, this middle part, that's the focal length we're dealing with. So assume this focal length, that distance, that gap, is 3.6 meters. 3.6 meters, and it can resolve objects on the ground. So this is the ground where we can have different types of objects that can be resolved. And so this object can be as small as 30 centimeters. That's how small the object can be. And if let's say there was a plane, an airplane flying, or maybe we want it to be a little bit higher. There was an airplane flying, and it has an open port. So the spy satellite can measure the size of that port. And our goal in this particular problem is to determine this diameter, the effective diameter. We want to see the diameter of this lens, assuming there is diffraction going on in this particular problem. Of course, with our light, with our bending light, lambda is 550 nanometers. So this is the information that's given in this particular problem. We're just going to jump and move on, and we see that the linear, the distance from the lens up until the ground is 160 kilometers. The focal length, f, is 3.6 meters. Of course, our lambda is 550 nanometers. Assuming this object is on the ground, so this is our small angle theta. So using small angle approximation, we get to see that small angle approximation, we get to see that theta equals to y over L. Of course, y is 30 centimeters, that's the size of the object. We can get that value. So, 30 centimeters times 1 meter over 100 centimeters. And then L is, of course, 160 kilometers. We want to change that to meters. 1 meter is 1,000. 1 kilometer is 1,000 meters. So we want to simplify that. 1,000 meters is the same as 1 kilometer. And this is going to give us a theta of 1.875 times 10 to the negative 6, assuming that's in radians for sure. So we go ahead and continue simplifying this problem. We get to see that theta is also the same as 1.22 lambda over d, which translates to 1.22. Lambda is 550 nanometers. Change that to meters. So we have 1 meter and 10 to the 9 nanometers. That's the equivalency of 1 meter. And of course, that's the value of theta. We can, instead of using this, and then we have over d. So we want to solve for d. We already have theta. So to solve for d, we'll use cross multiplication. So assume we have theta equals to 1.22 lambda over d. Multiply both sides by d, and then divide both sides by theta. So then we end up d being equivalent to 1.22. These two cancel, times lambda, which is 550 nanometers, times 1 meter is the same as 10 to the 9 nanometers. We already have a value of theta. If you go back up, you see it was 1.875 times 10 to the negative 6. So 1.875 times 10 to the negative 6. And so d becomes equivalent to 0.3579 meters. We can simplify that to d is the same as 35.79 centimeters. So once again, we had a problem, and in this particular problem, we wanted to find the diameter of the lens of a spy satellite, and the distance between the spy satellite and an object on the ground is 160 kilometers. The object itself lies 30 centimeters in size. The satellite can actually get the size of a port on a plane that's flying in a specific direction. Our focal length is 3.6 meters. That's our focal length, and we do know that the lambda is 550 nanometers. So we first of all solve for theta, which is using the small angle approximation because it's a huge distance, 160 kilometers. We get the value of theta is 1.875 times 10 to the negative 6. And then we use the relationship between theta and d to solve for d. And d, of course, is 1.22 times lambda over theta. And then we plug in the values and we get d is 35.79 centimeters. So hope you enjoyed the problem. Feel free to send any questions or comments, and have a wonderful day.